a unified methodology for the pre-silicon verification and post-silicon validation. The abstract, the growing importance of the post-silicon validation in ensuring the functional correctness of the high-end design increases the need for the synergy between the pre-silicon verification and post-silicon validation. We propose a unified functional verification methodology for the pre- and post-silicon domains. This methodology is based on a common verification plan and similar languages for test templates and coverage models. The implementation of the methodology requires user-directable stimuli generation tools for the post-silicon domain. We analyze the requirement for such tools and the difference between it and its pre-silicon counterpart. As based on these requirements, we implemented a tool called Treadmill and used it in the verification of the IBM Power 7 processor chip with encouraging result. Introduction. The size of the complexity of the modern hardware systems have turned the functional verification of these systems into a mammoth task. Verifying such systems involved tens of hundreds of person-years and required the compute power of thousands of workstations. But even in all this effort, it is virtually impossible to eliminate all bugs in the design before it tapes out. In fact, the statistics show that close to 50% of the chips required additional unplanned tape-outs because of functional bugs. Moreover, in many cases, project plans call for several planned tape-outs and intermediate stage of the project before the final release of the system. As a result, in implementation of the system on silicon learning at real-time speed is available. This silicon is used, among other things, as the intermediate and final vehicle for functional validation of the system. What is known as post-silicon validation. The post-silicon validation is not a new idea and has been used for many years in many places. It can be created with the finding of many functional bugs that escaped pre-silicon verification. However, in general, functional verification methodology for pre-silicon is still more varied and mature than for post-silicon platforms. Very little is published on post-silicon verification methodologies, and most research in post-silicon validation has centered on line checking and debugging capability of the silicon platforms. In recent years, we have seen more evidence that pre- and post-silicon verification cannot achieve their goals on their own with silicon in terms of finding all the bugs before tape-out, and post-silicon in terms of finding the bug that escaped pre-silicon. This creates an increasing need to bridge the gap between these two domains by sharing methodology and technologies and building a bridge allowing an easier integration between the domains. We propose a unified methodology for pre- and post-silicon verification. The methodology extends the established coverage-driven verification (CDV) methodology to the post-silicon verification domain. CDV is based on the three main components of verification plan comprising a large set of features in the DUV, design under verification, that needs to be verified. Random stimuli generated directed toward the verification goals using test templates, that is a general specification of the desired test structures and properties, and coverage analysis tools that detect the occurrence of the event in the verification plan and provide feedback regarding the state and progress of the verification process. So the unified methodology called for pre- and post-silicon to share the same verification plan and use similar language to define a test template in both domains, and the use of the same coverage models to ensure the status of the progress of the verification process. The methodology provides many advantages to users. It provides a commonality and enables sharing of the effort in creation of the verification plan. It can also facilitate mutual feedback between the two domains, for example, in the activity of the bug hunting. While our goal is to create a unified methodology for the pre- and post-silicon domains, the major differences between the platforms detected differences and the respective implementation of the methodology. One difference is that post-silicon platform provides significantly higher execution speed, which has the implication of the verification tools and need to adjust it for the best utilization of the available speed. See section 4. Another difference between the platforms is that common pre-silicon simulation platforms, including software simulator and hardware accelerator platforms, which perform the simulation on dedicated hardware and therefore offer much higher simulation speed than the software simulator. Support a detailed level of the observability into the state of the design as it is being tested. The silicon provides fewer opportunity to observe the behavior of the system. Therefore, bridging the gap between the pre- and post-silicon verification domains cannot be done blindly by copying the methodologies and technologies from the one domain to the other. So in fact, the limited observability of the silicon raises the need to use Accelerate as a third platform in the proposed methodology. In addition to the simulation and the silicon itself, the accelerators are fast enough to run simulation post-silicon tools and are observable enough to allow coverage measurement. This allows us to measure the coverage of the post-silicon tools in the silicon-like environment. So the focus of the paper is the stimuli generation of aspect of the unified methodology. We show how many of the concepts and the technologies that made constrained random test generators successful in pre-silicon verification can be adapted to the post-silicon domain. Specifically, we discuss how a user-directable tool that uses declarative test templates can be used in the post-silicon validation. And differences between the pre- and post-silicon platforms mean that we cannot simply convert a successful pre-silicon generator into a post-silicon tool. For example, to avoid spending too much time on generation compared to the execution of the test. The heavy sophisticated generation engine used in pre-silicon generators needs to be replaced with a lighter and much faster engine. In addition, to avoid long loading time, the post-silicon solution needs to be in the form of the accelerator. That is a tool that continuously generates test cases, execute them, and check their result. We implemented a proposed methodology in a tool called the treadmill. The treadmill is a bare metal exerciser. That is an exerciser that operates on the silicon itself without the support of the operating system. Treadmills fulfill the above requirement. It is a direct random generator with a simple and a fast generation engine. In addition, it meets the other requirement of the exerciser, such as providing mechanism to assist checking. Treadmill also addresses technical challenges, such how to replace the reference model, which is an essential part of both generation and checking the pre-silicon. So the proposed unified methodology and the treadmill were used for the time in the verification and bringing up the IBM Power 7 processor with the encouraging result. The use of the treadmill and other exercisers on the accelerator and provided significant help to the pre-silicon verification effort in finding many bugs. Some of them severe. The courage feedback at the stage provide a mean of the building a good set of the tested template for the bring up team, which helps ensure the smooth bring up and reduce the number of escape from the first tape out. In addition, in the user ability to direct the treadmill through the test template aided in the increasing some bugs found in the silicon in a pre-silicon environment, which helped analyze the fixed bug. So the rest of the paper is organized as follows. In section 2, we describe the main properties of the silicon-based stimuli generator as a reference. In Section 3, we define the requirement for a detectable post-silicon stimuli generator. Section 4 describes the proposed unified methodology. Section 5 is described the treadmill, our post-silicon detectable exerciser. Section 6 shows the experience with the unified methodology treadmill in the verification of the Power 7 processor. So the Section 7 is the concluded paper. The figure 1 is the test template and a corresponding test. Section 2 is pre-silicon stimuli generation. A pre-silicon stimuli generator has to provide the user with the ability to specify the desired scenarios in some convenient way and produce many varied high-quality test cases according to the user specification. The scenario specification known as a test template are written in a language that should enable an easy and accurate way from the specifying the scenarios from the verification plan. The figure 1 shows the example of the test template and define a table work scenario on the left and the example of the test generator from the test template on the right. And test template is written in a test template language of Genesis Pro, the IBM well-established test generation tool for the functional verification of the processors using a software simulator platform. The last of this section describes Genesis Pro approach to the test generation. So the scenario of the figure 1 starts with the store and then a sequence of the rows, each followed by either the air or a sub instruction. The memory allocation accessed by the load instructions are contiguous in memory as seen in the resource initial values section of the test. Address 0x100 to 0xF1F0. This is managed by the test template variable address. The use of the test template thus separates the test planning activity from the generator's development activity. The language consists of the 4 types of the statement: basic instruction statement, sequencing control statement, standard programming construct, and a constraint statement. Users combine this statement to describe the complex test that capture the essence of the targeted scenarios, leaving out the unnecessary details. The generated test cases must be valid according to the processor architecture and satisfy the user request specified in the template. In addition, they should also be different from each other as much as possible. This is done by specifying the rules determine the validity of the test cases. Of a test case, as well as the user request constraint. These generate or produce a test case by random sampling of the solution space to the resulting constraint satisfaction problems. The distribution of a generated test should not uniform, as we want to favor test and including interesting verification event. For example, register dependency, memory call region, especially ones that are extremely unlikely to occur under uniform distribution. This is done by the having analogy embedded in the generator, allowing it to bias random decision toward the stimuli that cause interesting event. The test analogy is defined the interesting verifications event, and including the stimuli that trigger them. As a result, add the stimuli for some interesting event depending on the processor state. The generator also employs the reference model of the DUV, so simulating on it every generated instruction. This way, the generator maintains an accurate view of all architectural resources and takes them into account during the generation of the interesting event. This scheme is shown in the lower part of the figure 2. Genesis Pro has been in use by the IBM for over 10 years. It's proven to be effective in meeting users' requirements, enabling them to write the test template, implementing the core verification plans of the IBM complex processors. Section 3, Post-Silicon Stimuli Generation. The characteristics of the post-silicon platforms and the differences between it and the pre-silicon software simulators dictate differences in the best way to use the platform for functional verification in general, and the stimuli generated specifically. The first information of the characteristics is the long loading and the initialization time of the silicon. Consider, for example, a test case of 10,000 instructions. Such a test case takes less than 1 millisecond to complete an advanced processor. On the other hand, preparing the processors for the execution, that is, performing a power-on sequence, loading the test case to memory, and etc., can take more than a minute. This results in an execution utilization for less than 0.002%. As a result, post-silicon validation tends to rely more on a longer learning solution. One commonly used solution of this type is use of the available applications, including the operating systems. Another solution is the use of exercisers, which are programs that are run on the DUV and exercise it by testing interesting scenarios. An exerciser is a self-contained solution. It generates the test cases, runs them, does the checking, and contains OS services required by the test cases. The exerciser runs on an endless loop, which makes it a good post-silicon solution since it is only loaded once on the DUV. The difference in speed between the pre- and post-silicon platforms affect the way the platform cycles are utilized. While pre-silicon test generators strive to use the scarce simulation cycles as effectively as possible by using extensive test technology and generate very high-quality test cases. The silicon platform is anything but short on runtime cycles. Therefore, to divert the resources from generation to execution, a post-silicon exercise should spend less effort in generating the precise, interesting scenarios and instead generate more general test cases using lightweight generators. Their loss of the precision is compensated by increasing in number of the tests generated. Another area where the pre-silicon platforms differ from the silicon platform is the level of the observabilities. This has a deep impact both on the ability to perform checking and the ability to measure coverage. The pre-silicon checking techniques include, for example, scoreboards and assertions, which depends on a high level of the observability into the design, which is not available in the typical silicon platforms. Similarly, the ability to measure the coverage of the silicon is very limited due to the low observability. We overcome this problem by running out the post-silicon exerciser on the accelerated platform, where the coverage can be measured as detailed in section 4. Another requirement for a post-silicon exerciser is simplicity. Hardware failures are hard to debug, and therefore simple software must be used case to the effort. In addition, we'd like to deploy the tools during the very early stage of the post-silicon validation effort when OS can be run on the DUV and operations such as reading files from an I/O device is unsupported. Another requirement is to keep the ratio between the time spent in generating and checking the test case and the time spent running it as low as possible. For example, while embedding a reference model, its exerciser could improve its checking capability. The reference model itself is complicated software that would significantly reduce the platform's utilization. Examples of checking techniques that don't use a reference model are mentioned in section 5. So section 4, the unified verification methodology. To better the integrated post-silicon validation to the overall verification process and improve each synergy with the pre-silicon verification, we need a unified verification methodology that is fed from the same verification plan source. A key ingredient for the success of such methodology is providing a common language for the pre- and post-silicon aspect of it in terms of test specification, progress measure, and etc. Figure 4 depicts such a methodology. This verification methodology bridges the three different platforms: simulation, acceleration, and silicon. The method requires three major components: a verification plan and directable stimuli generates suited for each platform and a functional coverage model. Note that the important aspect of embedding verification methodology, such as checking, are omitted from the figure to maintain a focus on the main aspect of our contribution, and namely stimuli generation. The verification plan includes a long list of the line items, each targeting a feature in the DUV and that needs to be verified. Each such feature is associated with the coverage event that the verification team expects to observe during the verification process and the method to be used to verify the feature. The verification plan is implemented using the random stimuli generators and produce a large number of test cases and coverage tools to look at the occurrence of the event in the verification plan. The random stimuli generators are directed toward to the verification goals by using test template. The test template aligns the generators to focus on the area in the DUV ranging from large generic areas like the floating point unit and to verify specific areas. Like a bypass between the stage of the pipeline and coverage analysis identified gaps in the implementation of the plan. Its feedback is used to modify the test template that do not fulfill their goals and create new ones. The expanding this methodology is to post-silicon validation is difficult because the limited observability of the silicon does not allow the measure coverage on the silicon. To overcome this problem, we leverage the acceleration platform to measure the coverage of the post-silicon tools. So the tool take advantage of the coverage information collected by the accelerator and use it to post silicon. Shortly before the first silicon samples come back from the fab, a regression suite of the exercise test template is created based on the coverage achieved on the accelerators. This regression suite is then used to continue the verification process on the silicon platform. With the unified methodology, we attach each of the line items in the verification plan, one of the more target platforms on which will be verified. These line items are converted to test template in the language and the generation tools used by each platform. A key ingredient for the success of the unified methodology is a similar operation of stimuli generators. In this sense, we would like to generators to use the same test template language, and when provided with the same test template, we would like the tools to produce similar, though not identical, test cases. Of course, the different platforms provide a different opportunity and put different constraints and requirements on the generation tools, but whenever possible, there are advantages to having similar tools. First, the pre- and post-silicon teams can share the task of understanding the line items in the verification plan and planning to ways to test them. In addition, the common language allows for easier adaptation of the test template from one platform to another. For example, when a bug is detected on the silicon platform, narrowing down the test template and hitting it on the simulation platform eases to the root cause of analysis effort. So it's important to know the difference between the platforms and also dictate the difference in the way the test templates are written in for the pre- and post-silicon tools. A test template could be a very specific and describe a small set of the targeted tests, or it could be more general, leaving more room for randomization. The validation engineers writing test template for a post-silicon exerciser must bear in mind for fact in the test template is used to generate a huge number of the test cases and again many processor cycles. To effectively these test cases, the test template must allow to test enough interesting variants. A test template is too specific, we really quickly run out of the steam and the silicon and start repeating the similar test. A pre-silicon test template, on the other hand, would typically be more directed to ensure the target scenarios are reached within the pure cycles available from simulation. 5. Treadmill. Treadmill was developed to enable the unified methodology described in Section 4, that is, to support a verification process guided by a verification plan by enabling validation engineers to guide the exerciser through the test template. The high-level tools architecture of a treadmill is depicted in Figure 2, along with the flow of the Genesis Pro, the polysilicon test generator tool described in Section 2. Like Genesis Pro, the main input to the treadmill is to test template data specified and describe scenarios for regions mentioned in Section 4. The template used for pre- and post-silicon tests have different characteristics. The test template language of the treadmill is similar to the language of the Genesis Pro. However, they adhere to the simplicity and generation speed requirements. Several constructs that require the long generation time, such as event, are not included in the treadmill's language. Other input to the treadmill include the architecture model and the test technology and the test system topology. Again, for simplicity reasons, many testing knowledge items are included in the Genesis Pro. Models are not used by the treadmill. The treadmill execution process starts with a builder application that runs offline to create an executable exerciser image. The role of the builder is to convert to the data incorporated in the test template and the architectural model and the data structures that are then embedded into exerciser image. This scheme eliminates the need to access files and the databases while the exerciser is running. The exerciser image is composed of the three major components: a thin OS-like layer of basic services required for treadmill's bare metal execution. So the representation of a test template, architectural model, and a subsystem and system configuration description as a simple data structures, and a fixed test template independent code that is responsible for the exerciser. The executable image created by the builder that are loaded into the silicon platforms, where the exerciser indefinitely repeats the process of generating a random test case based on the test template, the configuration and architectural model, and executing it and checking its result. So, in the case of the Genesis Pro, the test generation process is carried outside of the simulation environment, say on a dedicated server, and only the generated tests are loaded and run on the simulation platform. Simulation cycles would be too slow and allow the generation during the simulation. And the offline generation, on the other hand, can afford to spend time on a sophisticated generation and checking, and for example, by using a reference model as seen in Figure 2 for Genesis Pro. Treadmill test generation component was designed to be simple and fast. The generation is therefore static, that is, without a use of the reference model. A reference model is provided to generate information about the state of the processor before and after the generation of each instruction. This information is used for checking, but also to create a more interesting event. Loading the resources such as register can be partial replacement to the reference model, but this solution potentially interferes with the generation of requested scenarios. The for data-oriented event, such as divided by 0 or a simple yet effective solution, is to reserve the register to hold interesting values. Of course, the generator has to ensure that the result of the registers are not modified during the test. The execution of the same test case multiple times is used as a partial replacement for checking done by the reference model. This is done by comparing certain resources values, such as registers and a part of the memory, for consistency in different execution of the test case. Running the same test case multiple times may result in different results, even when the bugs are not present. For example, when several threads write to the same memory location, and the final values of this location depends on the order of the write operation. This requires a certain mechanism to be implemented in the generator to restrict the number of unpredictable resources. Although the multi-path comparison checking the technique is limited, it has proven to be effective when a control path-oriented bugs or bugs that reside in the interaction of the control and the data paths are concerned and increasing the probability of exposing such bugs. It is beneficial to introduce some kinds of variability into a different execution paths while making sure that variability maintains the predictability of the compared resources. This can be done, for example, by changing the machine code or changing the thread priorities. Section 6, Power 7 Experience. The proposed unified methodology for thread reward are used in a verification of the IBM Power 7 processor. The Power 7 processor implemented the 64-bit IBM Power architecture. Each Power 7 chip incorporates 8 SMT processor cores in 3 levels of caches, and memory and I/O controllers, and the other support and management logic. The process cores and out of order superscalar cores supporting up to the 4 stimulus simultaneous thread. Each core contains 12 execution units that are shared between the thread. This section highlights some of the results and lessons learned from the first use of the unified methodology, and Treadmill is a large industrial project. It focuses on the core verification of the Power 7. Power 7 was verified using the 3 platforms: simulation, acceleration, and silicon. Traditional silicon simulation-based verification was used throughout the lifetime of the project with the goal of revealing as many defects as possible. As soon as the core was sufficiently stable, an exerciser on oscillator B, E, or A, and the phase started was executed in the parallel to the simulation. Following every tape-out, a post-silicon validation phase started. This process was accompanied by the supporting effort on both simulation and acceleration platforms to assist the analysis of bugs that were initially detected on the silicon and verification of the bug fixes. The influencer of the unified methodology on the Power 7 verification started in the EOA phase. Exerciser and accelerators had been used in previous projects, but Power 7 was the first time in which the EOA effort was tightly integrated in the overall verification effort of the core. Each of the exercisers was assigned to over several line items in the core verification plan and was asked to provide test cases that covered the event associated with these 3 line items. The coverage method measured on the accelerator was incorporated in the project coverage report together with the unit and core simulation coverage. So the accelerator coverage was also used to harvest high-quality test templates for post-silicon validation. The Treadmill was not only exerciser used for Power 7. Several other exercisers were also used, and each of the exercisers was assigned to its own items in the verification plan based on its capabilities. Each exerciser created test cases for the verification items in its own way, and some exercisers were used modification of their base software. Others used parameters, tables, and macros for that purpose. The Treadmill was the only exerciser that used declarative test templates. This provided Treadmill with several advantages. First, it provided a convenient way for users to specify the desired scenarios. It also allowed ease sharing of the knowledge between the Treadmill and Genesis Pro due to the use of the similar language. Finally, it provides a means for easier transfer of the bug information between the platforms for bug creation and fix validation. And the use of the EOA provides several advantages to Power 7. The first, EOA process caught some high-impact bugs, One such bug detected by the treadmill shortly before the first tapeout was the show-stopper bug that would have totally undetermined the first silicon validation process and would have required 4 additional tapeout. In terms of the coverage, the EUA effort that obtained the results that are compatible with the core simulation effort. Table 1 shows the coverage result shortly before the first tapeout for the unit simulation, code simulation, and EOA. The table shows that the control-oriented units, such as the fetch unit, IFU, and a subsequencing unit, ISU, and EOA coverage is almost similar to the core simulation coverage. And this is an indication of exercise's ability to reach interesting scenarios even in a small number of acceleration cycles. Compared to the silicon platforms, the shared verification plan and the EOA effort gave a boost to the post-silicon validation phase. The organized verification plan and the hardest test template provided by Brain Update team with a good starting point to their effort and a means to track progress. The heavy use of the exercises in EOA also helped improve the readiness for the bring-up. All this supported a much shorter bring-up phase. In addition, compared to the previous project, a large percentage of complex bugs were found earlier in the bring-up process and the bare metal tools, which are easier to debug. The unified methodology and the similar test definition languages of the Genesis Pro and the treadmill provide another advantage of ability to hasten to the root cause analysis of bugs and validation of bug builds. This process produced a synergy between the platform where each task in the recreation, analysis, and fixed validation of the bugs was performed on the most suitable platform. For example, the relative speed of accelerators compared to the simulator was used to look around the complex bug found by Genesis Brewing simulation. This was done by generating and adapting the test template that produced the bug to the treadmill. Another example started with a bug that was found in the silicon. The test case that found the bug that was not found by treadmill and basic observations from the silicon causes the designers to speculate on a region for the bug. The next step was create a best template for treadmill on the accelerator to test that theory. When the bug was recreated on the accelerator, the test template was narrowed down and the bug was recreated in simulation. Finally, after the bug was fixed, all the test templates created for the first its recreation were used on the appropriate frame to ensure that the fix was corrected. That the success of a unified methodology was evident in the bug shift from the silicon to the acceleration and in the productivity improvement that it gave the post-silicon, acceleration, and pre-silicon teams. The verification of the Power 7 is considered by experts to be the best executed at IBM in the last recent years. The low number of the bugs that escaped to the silicon and escaped from the first to the second tape out provided good supporting the evidence of this. We believe that the our work has made a significant contribution to the Power 7 success. Section 7 Conclusions. The growing importance of the post-silicon validation to the verification process increases the need for synergy between the pre and post-silicon validation. Both pre and post-silicon verification methodologies and technologies. This paper represented a unified verification methodology based on a common verification plan and coverage models and that uses a similar test plan languages. To implement the methodology, we transferred and adapted to the pre-silicon stimuli the generation methodology in the post-silicon. In this transition, we maintained the concept of the directed random stimuli generator that is controlled via declarative, the test template. Other aspects, such as the trade-off between the generation smart list and generation speed were adapted to the better fit to the requirement of the post-silicon domain. The resulting tools, a bare metals exerciser called the treadmill, was used in the pre- and post-silicon verification of the Power 7 processor chip. Result of the experience to confirm our belief was beliefs about the benefit of the increased synergy between the pre- and post-silicon domains and using a directable generator in post-silicon validation. We see several ways to enhance the work described in this paper. First, we would like to extend the bridging the gap concept to the other aspects of the functional verification, such as checking and coverage. In addition, we are working to incorporate more testing knowledge into treadmill. For example, we are working to improve the treadmill, the ability to create interesting address translation paths. This will enable the treadmill to be better exerciser on areas such as cache coherence and the memory and I/O subsystems. Okay, thank you for your reading. Today I read this paper, A Unified Methodology for Pre-Silicon Verification and Post-Silicon Validation. Again, thank you for your time and thank you for your see you next time.